Imagine a day where you can simulate a world so perfectly that you can recreate every single neurosynaptic thought you could have, but now you're in the simulation on the computer.
What if everything around you, the chair you sit on, the sky above, even the very air you breathe, isn't real in the way you think? What if reality itself is a vast simulation, a digital construct so detailed and sophisticated that every atom, every thought, and every sensation is calculated? This is not just science fiction. It's a serious question that philosophers, physicists, and computer scientists are exploring. The idea has evolved from speculative fiction into rigorous scientific inquiry, probing the very nature of existence. Chapter 1. Bostrom's simulation argument. The modern discussion begins with Swedish philosopher Nick Bostrom. In 2003, he published a groundbreaking paper titled, "Are You Living in a Computer Simulation?" Bostrom didn't claim we definitely live in a simulation. Instead, he formulated a logical trilemma. One of three propositions must be true. Human civilizations go extinct before reaching a post-human stage capable of running high-fidelity ancestor simulations. Post-human civilizations choose not to run simulations of their evolutionary history or conscious beings. We are almost certainly living in a simulation, because if advanced civilizations both can and want to run simulations, simulated consciousnesses would vastly outnumber real ones. The logic is deceptively simple. If technologically mature civilizations create even a small number of detailed simulations containing conscious beings, the number of simulated minds would far exceed the number of original biological ones. Using the anthropic principle, which says we should consider ourselves typical observers when no reason exists to favor one scenario over another, Bostrom argues, if simulations exist in abundance, you are statistically more likely to be inside one than in base reality. This theory caught the imagination of both academics and public figures. Physicist Seth Lloyd suggested the universe itself could be a giant quantum computer. Entrepreneur Elon Musk famously claimed, "We are most likely in a simulation." And while such statements provoke controversy, they underscore how seriously this idea has entered scientific and philosophical discourse. Chapter 2. Evidence supporting the simulation hypothesis. The pixelated nature of reality. One of the most compelling arguments comes from quantum mechanics. Virtual reality is fundamentally digital, composed of discrete units or pixels. Remarkably, our universe exhibits similar characteristics. Energy, length, and time appear quantized, defined by the Planck scale, the smallest measurable units. Elementary particles and space itself may be discrete rather than continuous. Physicist Melvin Vopson describes this as a pixelated universe, echoing the digital structure one would expect from a simulated reality running on finite computational resources. Could this be evidence that our universe is encoded, calculated, and compressed like computer data? The second law of infodynamics. Vopson's work goes further. He proposed the second law of information dynamics, which suggests information entropy in the universe remains constant or decreases over time, in contrast to thermodynamic entropy that always increases. This principle shows up everywhere, in data compression algorithms, in biological systems like viral mutations, in atomic arrangements, and even in cosmological patterns. According to Vopson, the universe seems optimized to minimize information content, similar to how a computer reduces storage needs, a characteristic one might expect from a highly advanced simulation. Cosmic clues and the fine-tuning of the universe. While Bostrom's argument provides a philosophical foundation, scientists have explored whether physical evidence could hint at our reality being simulated. Some phenomena in cosmology, quantum physics, and information theory seem oddly consistent with a universe designed to be computationally efficient. Chapter 3. Cosmic Microwave Background Anomalies. The cosmic microwave background, CMB, the afterglow of the Big Bang, contains perplexing irregularities that challenge standard cosmology. Among these anomalies, the cold spot, a surprisingly large cold region in the CMB, The axis of evil, a strange alignment of temperature fluctuations across the sky, hemispherical power, asymmetry, uneven distribution of temperature variations. Some proponents suggest these could be glitches or compression artifacts in a simulated universe, akin to imperfections in digital graphics. While conventional astrophysics offers alternative explanations, these patterns remain incompletely understood, leaving room for speculation about the digital nature of reality. Chapter 4: The Fine-Tuning Problem. Another line of evidence comes from the universe's extraordinary fine-tuning. The fundamental constants, particle masses, force strengths, and dark energy levels, fall within incredibly narrow ranges that permit life. If these constants were even slightly different, stars, planets, and life as we know it could not exist. Traditional explanations include the multiverse hypothesis: countless universes exist, and we happen to live in one suitable for life. The designer argument: the universe was deliberately created with life-friendly parameters. The simulation hypothesis offers a third explanation: our universe's parameters might have been intentionally calibrated by a hypothetical programmer. In this view, the fine-tuning is not random or miraculous. It is purposeful, built into the code of reality to allow complex structures and conscious observers. Chapter 5: Information Theory and the Universe as Code. Beyond cosmology, the universe appears to exhibit information optimization. Vobson's research shows that information content across physical systems, from atomic arrangements to viral mutations, tends to be minimized. Gravity itself may be the universe's way of keeping information compressed, pulling matter into states of lower informational entropy. Biological systems evolve along paths that reduce unnecessary informational complexity. These patterns suggest a computational logic underlying physical reality, echoing how a computer program compresses data to conserve processing power. Could these be traces of a universal algorithm running behind the scenes? Chapter 6: Limitations and Scientific Challenges. Despite these intriguing hints, the simulation hypothesis faces enormous scientific hurdles. Energy requirements. Astrophysicist Franco Vazza calculated that simulating an entire universe, even just the observable portion, would require more energy than multiple galaxy clusters could provide. Even a simplified simulation of Earth would exceed plausible energy limits. Quantum mechanics. Entanglement and other quantum phenomena grow exponentially complex as particle numbers increase. Simulating this perfectly requires a quantum computer vastly more powerful than the universe itself, an infinite regression problem. Thermodynamic constraints. Computation produces heat. A simulated universe would generate enormous entropy, requiring energy dissipation that seems physically impossible over cosmic timescales. Consciousness. Even if physics could be simulated, can consciousness be recreated? Philosophers like David Chalmers argue it may require non-physical properties or unknown physics, which no simulation could reproduce. Chapter 7: The Energy and Computational Barriers. The most immediate obstacle is energy. Astrophysicist Franco Vazza demonstrated that simulating even a simplified version of our universe would require energy far beyond what exists in multiple galaxy clusters. Even simulating Earth alone at high resolution exceeds feasible energy outputs. Quantum mechanics compounds the problem. The phenomenon of entanglement, where particles become interconnected so that the state of one instantaneously affects the other, grows exponentially complex as more particles interact. Simulating these systems perfectly would demand a quantum computer vastly more powerful than the universe itself, creating an infinite regression scenario. The simulator needs quantum computers to simulate quantum computers ad infinitum. Thermodynamics adds yet another limitation. Any computational process generates heat. Maintaining a simulated universe over billions of years would require continuous dissipation of this heat, a task that seems physically impossible given the constraints of known physics. Chapter 8: Philosophical and Consciousness Challenges. Even if we ignore the energy problem, there remain conceptual hurdles. Infinite regression problem. If our universe is simulated, what about the simulators? Are they themselves in a simulation? This leads to a chain of simulations with no foundational real universe, a paradox that philosopher David Chalmers calls simulation regress. The consciousness problem. Can consciousness itself be simulated? While functionalists argue that replicating a system's functions reproduces consciousness, even proponents acknowledge that the subjective experience of consciousness might require non-physical phenomena. If consciousness cannot be replicated, then conscious beings like us cannot exist inside simulations, immediately falsifying the hypothesis for observers. Untestable nature. Perhaps the most fundamental critique is that the simulation hypothesis may be inherently untestable. Any observed glitch could just as easily be a natural physical anomaly rather than evidence of a simulation. If the universe is designed to hide its computational nature perfectly, no experiment can reveal it. Philosophers like Sabine Hossenfelder argue that unfalsifiable hypotheses have no empirical value and are therefore scientifically meaningless. Chapter 9. Evidence against the hypothesis. Physicists and skeptics provide rigorous counterpoints. Energy constraints. Simulating a universe with quantum-level precision demands impossible energy. Quantum complexity. Quantum entanglement grows exponentially, creating insurmountable computational barriers. Thermodynamic limitations. Sustaining a simulated universe over cosmic timescales is incompatible with the laws of physics. Infinite regression and consciousness. Questions of nested simulations and the nature of conscious experience remain unresolved. Despite these challenges, the hypothesis persists in popular and scientific discussions. Some argue that if a simulation exists in a universe with different physical laws, our physics-based constraints might not apply. But this moves the discussion into the realm of unfalsifiable speculation, which is not scientifically actionable. Chapter 10. Current scientific consensus. The scientific community remains deeply divided. Proponents point to evidence from information physics suggesting the universe is computational, quantum mechanics' discrete nature hinting at underlying bits or pixels, patterns of information optimization across biological and physical systems, technological trajectories indicating that future civilizations could, in principle, run realistic simulations. Skeptics emphasize energy and thermodynamic constraints making simulation practically impossible. Quantum computational barriers and infinite regression challenges. The problem of simulating consciousness, unfalsifiability rendering the hypothesis scientifically irrelevant. In other words, the evidence cuts both ways, leaving the question unresolved but endlessly fascinating. Chapter 11. The limits of knowledge. Despite intriguing hints, pixelated quantum behavior, information optimization, cosmic anomalies, and fine-tuned constants, the obstacles remain enormous. Energy requirements, quantum entanglement, thermodynamic constraints, and the complexity of consciousness make a fully simulated universe extremely improbable within the known laws of physics. Even so, some features of the universe suggest computational principles at work. The second law of infodynamics, proposed by Melvin Vopson, highlights the tendency for information entropy to remain minimized. The universe behaves as if it is carefully organized, compressed, and optimized, echoing patterns seen in digital systems. Whether this indicates a simulation or simply hidden laws of reality is still unknown. The universe could be operating on principles we have yet to fully understand, principles that merely mimic the logic of a computational system without requiring an actual programmer. Chapter 12. Living in uncertainty. Perhaps the most honest answer is that the question may be unanswerable. If a simulation exists, it is so sophisticated that we cannot detect it. If it does not, the universe still exhibits strange computational-like properties that challenge classical physics. Nick Bostrom reminds us that, regardless of the answer, our lives proceed the same way. Whether real or simulated, the experiences we value, love, discovery, creation, and wonder remain significant. The distinction between base reality and a perfectly rendered simulation may ultimately be philosophically irrelevant. Conclusion: the enduring mystery. The question of whether we live in a simulation straddles the boundary between science, philosophy, and imagination. Evidence exists both for and against it. Supporting evidence: pixelated quantum behavior, cosmic anomalies, information theoretic optimization, and the technological plausibility of future simulations. Opposing evidence: insurmountable energy demands, quantum computational barriers, thermodynamic limitations, consciousness challenges, and untestability. What we can conclude is not a definitive yes or no, but a deeper appreciation of the universe's complexity. Whether we are simulated or not, the universe operates in ways that are stranger, richer, and more intricate than most of us can fully grasp. In the end, perhaps the true value of the simulation hypothesis lies not in proving our reality artificial, but in expanding our curiosity, sharpening our science, and humbling our philosophy. It challenges us to explore, question, and marvel at the cosmos. A reminder that some mysteries, even if unsolvable, are worth thinking about every day.
So, simulation or not, the physics of our universe sets one hard boundary: aging. But scientists are now discovering ways to manipulate cellular time, from epigenetic clocks to Yamanka factors and senescent cell removal. You can click on the left side of the video where I break down how anti-aging science is moving from theory to real-world treatments. If you care about extending not just life, but healthy life, don't miss it.